All right, so Charles's law was named after a French physicist, Jacques Charles, and he was the first scientist to study the relationship between the volume of a gas and the temperature to which it's subjected. Okay, and he figured out that volume is directly proportional to the absolute temperature. So basically what this means is as one variable increases, the other variable increases as well. So in the example given, they say, okay, as temperature increases, volume will increase. So if we write that as a shorthand there, so when temperature increases, volume increases. Okay, conversely, if you decrease temperature, then volume is going to decrease. So what this means is if you increase the temperature of a gas, then the gas will expand. It will increase its volume. Okay. If you decrease the temperature of a gas, then the volume of said gas will also decrease. Okay. Now, where this can apply is, let's say you're making some fresh baked bread, and it's light and fluffy as a result of the action of yeast feeding off of sugar. Okay, now the yeast converts the sugar to carbon dioxide, which at high temperature causes the dough to expand because the volume of that carbon dioxide gas is expanding. Okay, so that's just an application in real life where Charles's law can apply. So the key thing here, and this applies to Charles's law, but also with any calculation that we do in this unit, that all calculations must be made with kelvins as your temperature unit and not degrees Celsius. Okay, so this notebook says that the reason why we do this is because there's no correlation between degrees Celsius and the temperature and pressure of gases, but also you do need to use the Kelvin scale because 0 on the Kelvin scale corresponds to a complete stoppage of molecular motion. So there's a better correlation when you use kelvins instead of degrees Celsius. What you need to know is always make sure you use Kelvin in your calculations. Okay. Now, with absolute zero, we briefly talked about it before. Absolute zero happens at 0 degrees Kelvin or 0 Kelvin. Okay, so I know that looks like okay, but that's supposed to be 0 Kelvin. And this is an important point because it's when all molecular motion has stopped because it's too cold for the molecules to move. Okay, so 0 Kelvin is equivalent to negative 273.15 degrees Celsius. Okay, so 0 Kelvin or absolute zero, that's the coldest you can possibly get. You cannot get any colder than that. Negative Kelvin temperatures do not exist. Okay, so the most important piece here is that absolute zero is when all molecular motion has stopped. Now, how do we convert between degrees Celsius and Kelvin? Well, you can use these formulas here. Kelvin is equal to degrees Celsius plus 273.15. Okay, and if you're converting from Kelvin to Celsius, then degrees Celsius is equal to Kelvin minus 273.15. So for myself personally, to remember like when to add 273.15 versus when to subtract, I always remember that Kelvin compared to degrees Celsius. Kelvin is always going to be the bigger of the two numbers, and you do need to know how to convert between Kelvin and degrees Celsius, because sometimes you'll get calculations where you're given the temperature in degrees Celsius and you need to convert to Kelvin in order to do the calculation. And then you also need to know how to go from Kelvin to degrees Celsius, because sometimes after you do a calculations, sometimes the question will specify, hey, I want my temperature specifically in the units of degrees Celsius, and that's when you'd have to convert from Kelvin to degrees Celsius. Okay, so let's do some sample calculations here. Okay, so we're converting degrees Celsius to Kelvin, so all you have to do is add 273.15 to these. Okay, so 27.0 degrees Celsius plus 273.15, that's going to give us 300.15 Kelvin. Okay, now if I was going to do this in the correct amount of sigdigs here, so for adding and subtracting sigdig rules, you always go with the least amount of digits after the decimal. Okay, so this would be 300.2 Kelvin with proper sigdigs. Okay, and then the rest of these questions will be like the exact same process. Add 273.15 and then make sure you put your answer in the correct amount of sigdigs. Okay. Now, in the second question here, we're given Kelvin temperatures and we're asked to convert to degrees Celsius. So this is when we're going to be subtracting 273.15. Okay, so absolute zero, that's going to be equal to negative 273.15 degrees Celsius. And if we put that in the correct amount of sigdigs, well, the number with the least digits after the decimal is going to be this one. So then that'd be negative 273 degrees Celsius. Okay, now if you're wondering how you'll remember this number, well, if you go to your Nelson periodic table and if you look in the second page in the bottom right hand corner, you'll see that it says right here that 0 degrees Celsius is equal to 273.15 Kelvin. It does say use 273 Kelvin. However, do not listen to that. Always use the number that has more digits in it so that your answer is more accurate. All right. Now, mathematically, Charles's law has two forms. They're both equivalent. It's just one looks a little bit different from the other. Okay, so you could use this form where all of the initial conditions, so the initial volume and temperature, they're on the same side, and the final volume and temperature are on the other side. Or you can use this one where there's kind of like initial and final volumes and temperatures are kind of mixed and matched in there. Personally, what I find is students have an easier time rearranging this equation, but you can use either or. It's just whichever one is more convenient or easier for you to use. Okay, and then as a reminder here, the 1s is equal to the initial conditions, and the 2s just mean the final conditions. Okay, so Charles's law, it's important to note that Charles's law only holds true if you have the same amount of gas, so same moles of gas, and if pressure is also held constant throughout the whole situation there. So with Charles's law, only temperature and volume can be the things that are changing. Amount of gas as well as pressure has to remain constant. That's what this part says right here. Okay, so getting into some examples here. So we have a sample of nitrogen gas that occupies a volume of 250 milliliters at 25.0 degrees Celsius. What volume will it occupy at 95 degrees Celsius? All right, so this first example gives us some helpful hints to get us started here. So as we've said before, whenever you do a calculation in chemistry, your temperature absolutely must be in Kelvin. You cannot use degrees Celsius. Okay, so I'm going to write my list of givens, and I'll worry about converting in a second. Okay, so our initial volume, that was 250 milliliters, and it's at 25 degrees Celsius. So I know these two numbers are connected. So because they come first, I'm going to say they're my initial conditions. So 25.0 degrees Celsius. Now I need to convert that into Kelvin, so I'm going to add 273.15, and that's going to give me 298.15 Kelvin. I'm not going to worry about sig digs here because this is not a final answer. All right, now since the question says what volume, that means we have no clue what V2 is, and the second temperature or the final temperature is 95 degrees Celsius. So let's go 95 plus 273.15. And that's going to be equal to 368.15 Kelvin. All right. So, like I said, you could use either of these equations here. Now, if you are using this formula sheet here, you'll notice that Charles's law is not on this formula sheet. However, we do have something called combined gas law, which we haven't gotten into yet. However, you can derive Charles's law from combined gas law. Remember that Charles's law states that pressure and moles of gas have to remain constant. Now, moles of gas isn't mentioned in this formula, however, pressure is. Now, if the pressure is the same, then that means P1 and P2 are the exact same value because pressure remains constant in Charles's law. So, what that means mathematically is that you can cancel out pressure, and now you have Charles's law. Albeit it's the one with fractions in it, which I find that students have a little bit more difficult time rearranging this. However, if you just cross multiply, then you can get the second version of Charles's law, which I find students have an easier time with. So V1 times T2 is equal to V2 times T1. So are you given Charles's law all nice, neat, and pretty on this formula sheet? No. However, you're given combined gas law, and both Charles and Boyle's law are kind of combined in combined gas law, and you can derive Charles's law out of the combined gas law formula. So long as you remember, pressure has to remain constant. All right. So what I'm going to do is I'm going to use the formula that students have a bit easier time with. So V1, T2. The trick is with this form is that you got to remember like the initial and final conditions, they're mixed and matched. It's not all the ones are on one side, all the twos are on the other side. All right. Now, for our question here, we have no clue what V2 is. So that means we need to isolate for that. Mathematically, what's happening between V2 and T1 is multiplication, so the opposite of that is going to be division. So we're going to divide by T1 because we want to get V2 by itself, right? So then if I write this all nice, neat, and pretty, we have V1 times T2 divided by T1 is equal to V2. Now at this point, I can plug in all my numbers. So 250 milliliters times by T2 was 368.15 Kelvin divided by 298.15 Kelvin. Okay, so what's happening with the units here? Notice that we have Kelvin on the top and the bottom. That means that they're going to cancel out, and our units for volume is going to be milliliters. Okay, so once we multiply this out, that's going to give us, hang on, I think I'm going to need to scooch this up a little bit. So when we take 250 multiplied by 368.15 divided by 298.15, what we get is 308.69528, blah, blah, blah. Keeps on going on forever. Okay, and that's milliliters is equal to V2. Now, the question doesn't specify what units it wants volumes in, so that means milliliters is fair game. Okay, so for sig digs here, if I look at all of my numbers here, they're all in 3 significant digits, so that means my final answer needs to be in 3 significant digits. So I'm going to count starting from the left. 1, 2, 3, there's my cutoff line. So 309 milliliters is our final volume. Moving on to the next example here, you have inflated your car tires with 9.8 liters of air on a cold winter day with a temperature of negative 20 degrees Celsius. After you have driven towards Vancouver for 8 hours on your winter holiday, the volume of the tires has expanded to 13 liters. What is the temperature of the air inside of the tires? So we're going to start off with our list of givens. V1, T1 is equal to V2, and then T2. Okay, so initially it says we put in 9.8 liters of air, and the temperature associated with that volume of air is negative 20 degrees Celsius. So I'm just going to automatically convert that into Kelvin. So that's going to give me 253.15 Kelvin. Again, right now I'm not worried about sig digs because this is not a final answer. Alright, now it says after we drove, the gas in the tires expanded to 13 liters and we don't know what the temperature is. Now, because the question doesn't specify if it wants temperature in Kelvin or degrees Celsius, either is fair game. So let's start off with our formula. I'm going to go V1 T2 is equal to V2 T1, and we want to figure out what T2 is. So then multiplication is happening between V1 and T2, so we need to divide by V1 so that T2 gets by itself. So T2 is equal to V2 times T1 divided by V1. Now let's plug in our numbers here. So V2, that was 13 liters. T1, that was 253.15 Kelvin. And then V1 was 9.8 liters. Okay, so notice how liters is on the top and the bottom. Those cancel out. Our final units are going to be Kelvin. Okay, so if I take 13, multiply it by 253.15, and then divide it by 9.8, what we're going to get here is 335.81122, goes on forever, Kelvin. Alright, so if we look at the given numbers in our question, okay, you might think to yourself, oh, well, there's the number 8 in our given numbers, so that must mean that our answer should only be in 1 sig dig. No. Okay, the reason being is because we didn't use 8 hours in our calculation. So that's why our final answer isn't going to be in 1 sig dig. We need to look at the numbers that we actually used and use the number that has the least amount of sig digs, which will be this one, because it has 2 sig digs. Everything else has 3 sig digs. So for 2 sig digs, so if I just write 2 sig digs there, if I count from the left, 1, 2, that's my cutoff line. Okay, but notice how 335 is not the same as 34 Kelvin. Okay, so we need to make sure that we are using scientific notation in order to represent this number. And an easy way to know when to use scientific notation or not, it's usually whenever your cutoff line comes before the decimal point, you're going to have to use scientific notation there. Okay, so for scientific notation here, we need to move the decimal so that there's only 1 digit in front of it. So I need to move this decimal over 2 spots over to the right. Or sorry. So I need to move this decimal 2 spots over to the left. So 3.4 times 10 to the power of. Now we need to decide if our exponent is going to be positive or negative. Remember that if your original number is bigger than 1, your exponent's going to be positive. If your number is between 0 and 1, then your exponent is going to be negative. So in this case, because 335 is bigger than 1, that means our exponent has to be positive. Okay. Now, I'm just going to take a moment to write out what I said about scientific notation, just so that we get these in the notes. So, for scientific notation, so if the original answer is bigger than 1, exponent is positive. If the original answer is between 1 and 0, so it's 0.258 or something like that, exponent is negative. So the exponent will be negative when you convert your answer from just like a regular number to scientific notation. So heads up on that. Now, if you really wanted to put this in degrees Celsius, you could. And if you wanted to try that out for yourself, you can. All you need to do is just subtract 273.15 from your original number and then round off to sig digs. Okay, and that would give you 63 degrees Celsius.